with regards to questions, if you have any questions while we're talking, feel free to ask them, because I realize that sometimes the moment can pass and you can forget them. And I'm also a strong believer that there are no stupid questions, particularly when it comes to geophysics, for reasons that hopefully will become apparent very shortly. Am I still sharing the screen? Is that still working? I noticed. Okay, perfect.
Yeah.
Okay, so yeah, thanks very much. I work with Atkins. I'm a principal geophysicist with Atkins. I started working there in October last year. And prior to me starting, and my colleague Edward Cox, there wasn't really much in-house expertise across Atkins. So one of the things we've been trying to do is build up our kind of in-house capability to specify and interrogate and understand geophysical models and data for the use of ground engineering, particularly in the area of mapping hazards. And I'm going to talk to you today a little bit about a particular case study, which is the one that's on the screen in front of you, looking for karst hazards in the east of England. But what I'll do before that is I'll just give a little bit of a background about geophysics, really try and make the case for geophysics, why we want to use it. And rather than talk to you about individual methods or why we use particular things, I really want to talk to you about geophysics and its place within this kind of rise of 3D geoscience. We're seeing, digital applications being used in ground investigations and site investigations, and really try to place where geophysics sits in that sort of sphere. So I'll do a little bit of introduction about that, and then we'll talk a bit about why you might want to use geophysics for things like site investigation, talk a bit about what geophysics is, and again, I'll stick to very broad concepts rather than zooming in specifically on any one technique. And then after I've kind of confused you and baffled you and given you a good list of reasons why you shouldn't use geophysics, I'll then recap why you should use it again before I go into the case study that I want to talk to you about today. And what we'll do there is it's a case study specifically using resistivity, which is a geophysical method. So I'll give you a little bit of an overview of that one in a bit more detail. And then we'll have a roundup of the case study. And please, like I said, questions at the end, or if you feel you have a question as we're going through the talk, then please just let me know and we can address it. So as I said, I'm going to start off by making the case for geophysics. This is a survey we did on a railway, as you can see, back at the end of last year, looking for sort of precursory conditions to slope failures in the cuttings of the Bluebell Railway down in Sussex, using a combination of resistivity and seismics, and also drone information for that one as well. So to set the context for this talk, what we've got here is a timeline. Along the top, we've got the developments, or what I think are the major developments in kind of 3D and remote sensing applications that we've seen being used for various ground engineering applications over the years. And along the bottom there, we've got sort of corresponding developments in geophysical technologies as well. So this stretches back to about the last sort of 150 years or so. I think it's really interesting that the first image there on the top left is a stereoscopic image. So this is 3D data that we've been acquiring, going back to, like I say, 150 years of sites. We've been able to have that visualization of what's going on the ground surface from 3D. And that's developed over time, as we move into the sort of early 1900s with things like the two world wars and the need for high resolution aerial photography. We've seen a big increase in the use of aerial photography for land use assessments and understanding geomorphological features. And that has continued through, again, the use of 3D stereoscopic imagery from those data sets before the advent of things like spot satellites in the 1980s, the development of 3D rasters, introduction of this technology coupled with geographic information systems and the ability to actually see things in 3 dimensions in a digital environment. And then we arrive at where we are today, which is where I think we've got a far more bespoke approach to acquiring digital technology from sites. So we're all increasingly familiar with drone technology, the sorts of things it can do, whether it's using LiDAR or structure from motion to understand the surface representations of sites and using that data in a digital environment to really understand what's going on. And the example on the right there is taken from a landslide up in North Yorkshire, the Holland Hill Landslide Observatory. And you can just see straight away from that data set the kind of key geomorphological features of the landslide, just from having a high resolution digital terrain model, which was produced from a drone. So along the bottom there, we've kind of got corresponding developments in geophysics. So right back to the days of kind of britches and floppy hats, when people were going out with analog methods and trying to understand what the conditions were of the ground using non-intrusive methods, through to big developments in the 1980s in computational geophysics. So actually being able to perform complex inversions using computer technology, and that really took off in the 90s with the development of many of the commercial software packages that we still use today. So the image here in the middle of the cross section is from a program called Res2D INV, which is for the inversion of two-dimensional resistivity tomography data, and that's one that you'll still find used in many consultancies across the UK and America and beyond today. And then very soon after that, the development of three-dimensional inversion technologies, which is really where I think something has not been adapted very well for the commercial use today, and it's one thing we're going to discuss in the case study later. And perhaps the most recent developments have been the application of four-dimensional technologies in geophysics. So this is the deployment of monitoring technologies to look at how the ground and the subsurface changes over time using non-intrusive ground investigation methods, something I could talk about at length for a long time, but today I want to focus on just the 3D, the snapshot environment, and talk a bit about the use of that in ground engineering. So why geophysics? I mean, I'm not entirely sure what the makeup of the audience here is, but hopefully you've all got a sort of understanding of the main aims and objectives of undertaking a ground investigation in a commercial context. What we'd normally do when we want to understand what's going on the ground is we would traditionally commission some sort of intrusive investigation. Normally involves getting a drill rig like that or some sort of trial pit, intrusive information from the subsurface, and the more information that we get, the more expensive it becomes, but obviously the better the picture that we have of what's going on in the subsurface. And of course, there comes a point where perhaps the budget runs out, or we feel confident enough in our interpretations that we can extrapolate the information we've got and maybe make some rudimentary interpretations of that. But the question I'm going to be constantly asking today throughout this talk is the ground fully characterized from the data that we have? And is the risk to our design minimized? And I think that's something which I personally feel that the use of geophysics in the UK, particularly in the last sort of 10, 20 years, has focused very much on two things. It's either been a tool for planning your intrusive investigations, so a means to an end in terms of actually working out where you're going to get the maximum cost benefit of putting your boreholes in your trial pits, or it's been used as an afterthought where perhaps something has been found during those intrusive investigations which was unexpected. So whether that is some sort of geohazard or some sort of problematic ground for engineering purposes. So we're going to try and think beyond just the scope of the ground investigation and what the information we have actually means for the design of whatever it is that we're trying to achieve by the ground investigation. So whether that is a design of a structure which is going to be placed, or an excavation, or any kind of use of the ground in the future. So my argument would be that in this case, is the ground fully characterized? I don't think it is. We've got some pretty hefty uncertainties in that interpretation. And is the risk to design minimized? I don't think it is, because of the latter point. We don't fully understand the character of the ground. So if we went back to the start and said, well, let's try and use some geophysical, some non-intrusive methods, what would that look like? So it might look like the deployment of a resistivity system. So here we have a series of electrodes which are hooked up to a resistivity meter. And what we're going to do is inject a current through the ground at a series of points along that electrode line to build up an image of the resistivity of the subsurface. And that might tell us something very fuzzy about the ground surface that we're not completely certain about, but it might give us a better site scale overview of what's going on compared to just having a handful of boreholes. Now, any good geophysicist hopefully will tell you that this isn't something you should do in isolation of ground investigation. So what we then always suggest would be to go in and use some intrusive methods to try and prove that, to try and understand if you can increase the resolution or increase the confidence in the extrapolation of the information that you have. So this integrated approach where we're using, maybe taking some of the budget from our intrusive ground investigation and allocating that for a non-intrusive survey to get that site scale overview, it is really where we are at the moment. And I think the site scale context, we talked about, or I talked about remote sensing being in the beginning of this, that we've kind of got used to looking at big data sets from remote sense sources, whether it's satellites or drones, Google Maps, all these sorts of things. We're used to looking at, as engineers, we're used to looking at boreholes and very small measurements of the subsurface, but we don't tend to think about the subsurface operating at the same scales as some of these big data we get from remote sensing. And really, my colleagues are increasingly encouraging me to talk about geophysics being like remote sensing of the subsurface, and it's a kind of analogy I'm not always comfortable using, but if it means it gets the point across, then I'm quite happy to accommodate it for talks like this. So what is geophysics? I mean, we've talked about the fact it's non-intrusive. geophysics essentially means that we are trying to measure some kind of signal in the ground, and that signal hopefully has got some correlation with a property that we're interested about. The signals that we're interested in can either be artificially generated, so in the example of a sort of traditional seismic refraction or reflection survey, there'll be seismic signals that we've generated using either a sledgehammer or some kind of explosive source or a vibroseismic truck, and we're trying to measure something about that signal, whether it's the velocity or the two-way travel time, to understand the properties of the ground beneath where we have our sensors. Or alternatively, it can be the measurement of naturally occurring or passive signals, which tell us something. So that could be magnetic fields, or it could be gravitational fields, and these can be used to look for ferrous hazards in the ground, or they can be used to look at differences in density when it comes to gravity of the subsurface. The primary and biggest benefit of geophysical surveys is they're non-intrusive. So if you have hazardous ground and you're trying to understand something about it and you're not sure where you're going to put boreholes or intrusive methods, then you have a means of being able to do some kind of scanning in advance. And I would use the analogy of doing a sort of MRI scan before doing brain surgery. This is a way of trying to look at the whole problem that may be posed by a site and trying to understand in the broadest terms what the distribution of risk might be before you then go and actually go inside and have a look. I certainly think that if I was going to sit, or be lying on a table having lined up for brain surgery, I'd want them to have some sort of, idea of what they were doing before they went in and did their intrusive investigation. And the main benefit is that geophysical surveys are relatively inexpensive, and they're inexpensive in terms of the amount of data that you can get for the amount of time you spend on site when you compare them to sort of intrusive investigations. Now, that doesn't cover necessarily equivalence of uncertainty, and that's something that we'll touch on in the case study later on. But the final thing is that they're multidimensional as well. So you have the ability to acquire data in 1, 2, 3, and as I mentioned earlier, 4 dimensions. And this can be really suited to the needs of the site that you're trying to understand. And in the particular case study I'll discuss later, we used a 3-dimensional approach, which for understanding the karst geohazards on the site was very well suited to understanding what the potential risks for development were. So you'll notice that this list of limitations I'm about to go into is significantly longer than the benefits I've just outlined. The main limitation is that most methods have got a limitation in their depth of investigation, or they have a significantly decreasing resolution with the increase in depth. So you're going to understand what's going on in the near surface to a much higher degree than you are going to understand what's going in the deep subsurface. And that can be problematic on some sites. If you've got, for example, if you have surface expressions of some geohazards, for example, karst or sinkholes, that can be quite easy to understand using geophysics. If you have sort of, for example, deep halite dissolution where you have quite small voids developing at depth, that can be far more difficult. And it's one of the main considerations when planning a geophysical survey is what the depth investigation is, how much you have to tailor your survey to be able to understand the sort of critical depth that is required by the investigation. The other main limitation is that they do require a measurable contrast in some property of the ground, and that's in relation to the type of signal you're trying to measure. So a good example of this would be if you're looking in an environment where you have 2 rocks that are very similar densities that maybe have very different mineralogical contrasts or compositions. But if they have very similar densities and you're trying to use something like a gravity survey, the gravity isn't going to differentiate between the mineralogical content of those 2 rocks. It's only going to see a similar density. So you'll miss some of the main contrast that you're looking for because it doesn't exist in that geophysical property. And that's why we tend to use multiple methods when we're investigating sites, because we want to try and cover as many of these sort of geophysical similarities as possible to make sure we're getting the full geophysical suite of understanding of the ground. But the basic principle there is if there's no contrast in terms of the geophysical signal you're trying to detect or measure, then you're not going to find anything in the ground. And related to that is the fact that the signals we're looking at, how they vary in the ground, is rarely directly related to how the property we're interested in varies throughout the ground. And this is also closely related to the idea that the geophysical measurements can be sensitive to more than one property. So a good example of that is that resistivity, for example, if you put an electrical current through ground and that ground has increased moisture content or perhaps has an increased clay content, both of those things are going to cause a drop in the resistivity. but it won't be possible necessarily just from the resistivity survey alone to know which one of those is actually causing the drop. So you need to then do some other investigation methods, whether it's intrusive or further geophysical methods, to try and deconvolve these two signals and work out what is actually the causative factor of your geophysical signal. I think these last 2 points are probably ones that are least understood when it comes to the commercial sector. The first being that measurements, geophysical measurements, are subject to errors at many different stages in their acquisition. So unlike a sort of FDEM model where you're taking assumed properties and plugging that in and you know you have errors associated with the model, or unlike a laboratory test where you just have errors that are associated with the measurement, you actually have both of those things happening in geophysical data. And that's because we have to go out in the field and we have to actually acquire the data, and there could be errors associated with being on site, difficult ground conditions, inexperienced staff, faulty equipment, which are going to introduce errors at the data acquisition stage. And then when we get that data back to the office and actually have to start looking through that data and processing it and filtering it, we may start introducing errors at the point that we are manipulating the data. And finally, particularly with the methods that tend to look at the ground in two-dimensional cross sections, and we'll come on to that in a second, we have to go through this process of inversion. And inversion is basically taking the measurements that you've got from the ground and then trying to create a model that fits those measurements. And it's best described, I think, by if you were to take a bar magnet and you knew the dimensions of the bar magnet and you knew how intense the magnetic field or the magnetic susceptibility of that bar magnet was, you would probably be able to easily forward model what the magnetic field of that magnet would look like in 2 or 3 dimensions. What we've got with geophysics is that we have the magnetic field, but we don't understand the properties of the bar magnet. So we're trying to iteratively create a bar magnet, an imaginary bar magnet that would fit that magnetic field lines that we've got. So we're trying to back calculate, as it were, from our magnetic field what the bar magnet looks like. And that's the process of inversion. We're trying to basically understand the ground conditions from a bunch of signals that we've got, which may have many, many different models that would actually propose the same solution. So for that reason, we have to go through this process of inversion, which is a model. And I think there's not a great understanding that with often a lot of geophysical data, what we're seeing is a model of the ground or a model of the geophysical measurements, and we're not seeing direct measurements of the ground itself. So it's something I'm going to keep saying in every presentation I give, and hopefully eventually everyone will get a grip on that. But it's something I think is not well understood in the sort of ground engineering community at the moment. Okay, so I alluded to already that the list of limitations I've gone through there is significantly longer and more complex than the benefits. So what I'll do now is I'll just go back and we'll talk about why we should use geophysics. But I'll just remind you of this quote, which I'm sure you've all heard from George E.P. Box, which is along the lines of all models are wrong, but some are useful. And really what we're trying to do as geophysicists, particularly in the commercial, ground engineering sector, is to make sure that the models we have are as useful as possible and are as least wrong as possible. That's really our kind of mission statement as I see it. So this is a great diagram. This was produced by Rod Edison Fugro and was provided by my colleague Ed Cox, who's working for me or with me at Atkins at the moment. And what it shows here is the degree of uncertainty associated with the type of geophysical approach you're taking to the site. So uncertainty on the vertical axis and the time and cost and effort as you move down this sort of suite or approaches in geophysics used for ground investigation. So on the left there, you'll see that we've got what we call, what Fugro referred to as digital site screening. And this is really the kind of most rapid and broadest scale approach to understanding what's going on the ground. It typically involves the use of instruments that can either be walked, they're non-contact with the ground, or perhaps in the case of ground penetrating radar, you're pushing a trolley along the ground. And occasionally some of these things can be mounted to the back of things like quad bikes to get even better coverage of the ground. And there's lots of work being done at the moment looking to see if it's possible to mount these things onto drones as well, to see if you can get even more coverage and sort of greater extents covered in shorter amounts of time. But these tend to give you a very broad overview, typically in sort of two-dimensional map type views like you can see here. So this is an example taken from a site survey. You've got 2 obvious linear features there which relate to buried services. But perhaps more interestingly, just down in the kind of southeast of the site here, this very, very low conductivity zone, very high conductivity zone, which is associated with the blue color here, is actually, and it's very difficult to see because it's a large site, but there's actually a mining adit there. And there's a linear feature just in here, which is the extent of the mining adit leading to an abandoned shaft. There's also evidence, if you zoom into this, of sort of UXO distributed across the site as well. And of course, the general background change in geology, which you can see represented by the transitions from broad scale blue to sort of green and yellow areas as well. So this is the kind of first stage of geophysical reconnaissance data that we use if we're looking to do a full site investigation, something that tells us a lot about the site in a very short amount of time, but perhaps is limited in its kind of dimensional attributes. So this is just a two-dimensional representation, and we have to make a qualitative interpretation of how deep we think these things are based on that information. The next step would be to go and do sort of more detailed cross-sectional type investigations. So on the screen in front of us is an example of some resistivity surveys that have been done at a site looking at sort of trying to map bedrock geology, but in a landslide context. And what we can see here is that there's a pretty stark transition between some of the lines that are existing towards the kind of north of this one left-hand side of this gully, should we say, and just beneath the road there. And we think that's probably because there's a sharp transition in the bedrock that exists between these two lines. But then also across this gully as well, we can see that generally speaking, the lines on the right-hand side of the screen have got much, much lower resistivity, which leads us to think that we've got some sort of fault-controlled system where we have a change in bedrock across this divide. So as well as resistivity, we can use things like seismics, and we can use that to produce these two-dimensional sort of images of the site, which can be very useful for doing between boreholes or sort of tying in with other sources of intrusive information to get a really good understanding of how the ground varies between two locations. We then got sort of surveys which are designed to give a far more specific measurement of a much smaller area. So these are typically in situ type measurements, and the example given on the screen there would be a sort of downhole or wireline log, looking at things like seismic velocity in a borehole or density within a borehole, which can then be used to make estimations or calculations of sort of elastic modulus, including elastic moduli, including sort of shear Young's Poissons and so forth. Usually used for the kind of design elements of projects once things have got further down the line. And finally, what we've got here is an example of what Fugro referred to as 3D geodata. And I think this one's really interesting because this is the site model now. This is where we're starting to get information at the site scale that tells us something about the distribution of properties or geohazards within the ground. This is usually done by acquiring high resolution three-dimensional data on sites. It can take a lot of time and can be quite labor and computationally expensive. But usually you get a much better result if you are able to sort of justify using this approach. And I think, in my opinion at least, well, actually, before we do that, I would just say that, you know, the way that these things are effective is very, very dependent on a lot of factors. Where they're done badly, it's because we tend to see bad specifications or unsuitable or unnecessary methods being used. Just gonna oh, sorry, just had a message come in there. So yeah, we've got unsuitable methods, perhaps like I alluded to before, poor processing or you know, inexperienced people using equipment. But when it's done well, you can see that it's very easy to reduce the amount of uncertainty for not as much time and cost and effort. And I think the case that I'm really trying to make today is probably that this 3D geodata approach at the end here, which is being touted in this diagram as perhaps the highest amount of time or cost or effort, actually, I think you can bring this into the sort of workflow of how we use geophysics at a much, much earlier stage, and hopefully with greater benefit for the long-term cost and understanding of risk on projects. Okay, so that's kind of the broad overview. I guess at this point, if anyone has any questions on the kind of background, I'd be very happy to take them. Just if there's anything we want to mull over before we kind of move on to the sort of more specific case study. But if there's not, I'll move on. So what we're going to talk about now is the Welby Tank 3D resistivity survey. And this is an example of the 3D geodata approach that I sort of mentioned in that last pipe there. So Welby Tank is literally a water storage tank that's going to be built as part of the Strategic Pipeline Alliance, which is a project headed up by Anglian Water to refresh hundreds of kilometers of pipelines across the east of England. And a lot of these sites that they're looking to develop have significant hazards when it comes to the presence of karst. So you've got dissolution, potential sinkholes, but you've also got eroded bedrock because of the glaciofluvial erosion that's occurred at these sites as well. So as well as potentially having dissolution, you've also got very, very differential thicknesses of glaciofluvial material, which is much more clay rich compared to the hard limestone that it's sitting in. So the risk of differential settlement when you're looking at building large structures is quite apparent. And this project's been undertaken for a couple of years. So it was in existence before Atkins had a sort of dedicated geophysics team. So the phase one was commissioned by Atkins. It was a geophysics consultancy or contractor was brought in. And that comprised doing some resistivity surveys along the red lines that you can see on the screen here. So pretty broad scale, about 50 meters between them, but very good site coverage, covering the majority of the site. And the main question that was being posed there was, can you understand the distribution of these glaciofluvial materials and the presence of potential sinkholes? And after that, there was a round of intrusive investigation. So initially, the structures which you can see here were actually planned to be built in this field to the west, but they decided that actually they managed to confirm the extent of glaciofluvial material which was mapped by the BGS, and they wanted to avoid using that particular field, and they opted to use the field in the east instead. But the initial geophysical survey didn't have much data in the west of the field, in the east of the field, so they wanted to go back and do some more resistivity fill-in lines, and at that point, we had come on board with Atkins and we said, well, actually, we think this is a really good case study or a good opportunity to use some three-dimensional geophysics to get a three-dimensional model of the ground, to better understand the distribution of potential geohazards. And then the final phase, which we haven't had the results back from yet, is actually the follow-up intrusive investigation. So to look at these phases in a bit more detail, the initial geophysical survey that was undertaken, I mentioned it was done using resistivity, so you can see where you've got the resistivity lines mentioned here. There's also an electromagnetic survey done as well. So this is the broad scale two-dimensional mapping done from the surface using a non-contact instrument, which was, I think, probably dragged across the site using a quad bike, and you can see that there's broad correlation between where you've got these high conductivity blue colors with the location of the glaciofluvial material that has been mapped by the BGS, which is where you've got these pink polygons in the background there. So it was this survey that initially prompted people to say, well, we think we should relocate to this area of the field. But as you can see, there's quite a large gap in the electromagnetic survey towards the east of the site there. It's worth saying as well that the resistivity survey came back, and this is a view looking towards the northwest of the site here. And I think it's a lovely image, to have these sort of fence diagrams and things. And you can certainly see where in the northwest of the site you've got these again dark blue colors, which show you've got variable thicknesses of this glacial fluvial material, and where you have these kind of reds and almost purple colors is where you've got much more resistive material. So it's probably worth just saying at this point that the general theory when it comes to limestone and dissolution and karst is that where you have intact bedrock, where you've got intact limestone, you tend to see intact pore structures which are going to increase your resistivity. So very, very resistive values typically associated with intact strong limestone, grading down to sort of medium sort of values, which in this case is represented by about 400 or 500 ohm meters, would be suggestive of perhaps having some kind of dissolved content or some sort of fracture network that maybe is left in water throughout the limestone. And then where you've got these very, very low figures, which are going down to sub 100 here, is where you've got presence of clay infill, or perhaps lots of water in the system as well. So this is a good diagram, but the question I mentioned previously was, from this diagram, is the ground fully characterized and is the risk to design minimized? And I would still actually argue that the answer is no on both counts. And the reason for that is that we know this is a site that has potential dissolution features in it, potential sinkholes. Those sinkholes are probably going to exist on the order of 3 to 4 meters maximum. So do 50-meter spaced electrical resistivity tomography lines actually tell us much about the distribution of those? I haven't done the calculations on the probabilities, but I think there's far more of the site here which is not covered using geophysics than is covered. Even if you've got the surface electromagnetic survey, which was done in the pink box on this figure, you still have many areas of the site which maybe you're not getting full geophysical data coverage. And because of that, I don't think the risk to design has been fully minimized. So that's why when we were asked to come back and consider doing more geophysics on the site, we said, well, look, we think you should probably consider doing a 3D approach. But prior to the time that we did that, there were some boreholes drilled. And I'm just showing the boreholes. You can probably see just very faintly in the outline here. This is the field to the west and the field to the east. Because they've made the decision already to move the structures to the eastern field, I'm just going to focus on the intrusive investigation that was undertaken in the eastern field. And when they did their investigation using these 4 boreholes, they came back with showing that generally speaking, you've got weaker or medium weak limestone present in the north of the field that tends to increase in its strength as you move towards the south of the field. So suggesting that actually you probably have mostly good ground, perhaps with some areas of slightly weaker limestone existing in the north. Again, is the ground fully characterized? Is the risk design minimized? Well, we might know a bit more about the quality of the rock which is in the ground, but we only know a very small amount about the area that we're trying to investigate. So this was at the point we said, well, look, we think you should go back and we should do a 3D resistivity survey. So rather than having these 50-meter spaced lines, we'd recommend they're on the order of about 8 meters. And we want to do far more coverage of those lines. So this was actually an occasion where we hired in the equipment in-house, and my colleague Ed Cox went and acquired these extra data lines. We reused the existing Terradat data, or the data that had been acquired by the geophysical contractor, so we didn't have to repeat that. We were building that into our new survey. And we managed to basically cover this field in the space of about 4 days and process the whole thing in about 2 weeks. And using this, we've got a 500,000 meter cube model now, which we have of this site. And what we can do is, like I said, we go through a process of inverting that data. And now, rather than having just 4 borehole points and a sort of fence diagram of sparsely positioned resistivity, we've now got a 3-dimensional block of data that we can start slicing and looking at the different dimensions of. And one thing I think that's really, really interesting about this, and a complete coincidence, was that when they drilled these 4 boreholes, you can see that as you get down to depth here, the sort of 15 to 20 meter range, you've got these very dark reds which are occurring along these 3 boreholes here. And you'll remember that there was a general kind of consensus that the ground maybe was stronger in the south and maybe a little bit weaker or medium weak as you got towards the north of the site. Well, actually, it looks like that they happen to have just placed these boreholes on what we would consider to be the resistivity maxima. And again, if you remember that we were saying that conventional resistivity theory would say that where we have increases in resistivity is where we have the strongest limestone on site, because we've probably got the most intact limestone. So you can see here, particularly in this area, in this area, in this area, you've got these increases in limestone, but actually the ground between these 3 boreholes in particular seems like we've got something which is quite low conductivity at depth, and that could be the presence of clay because you've got some sort of solution feature infill, or it could be associated with direct dissolution of the limestone itself and the breakdown of pore structures, ingress of water. There's lots of reasons, as I mentioned previously, as to why that could be. So at this point, we had 2 options. One was to go back to our client and say, look, we are the geophysicists, we are the experts, and we think this is what this is. But we didn't want to do that. We wanted to try and sort of bring them along on the journey a little bit. So what we did was we took the 4 boreholes that have been drilled, and we basically extracted the resistivity profiles from those locations. So what we're seeing here, just for the moment, we just ignore the red and the blue lines, which are on the left-hand side of this plot. We've got the 4 boreholes, and we've put symbols around that where we've got the presence of weak, medium, or strong limestone. I think what's interesting is that generally speaking, where you've got the strongest limestones on site, particularly between this kind of 6 to 10 or 15 meter boundary, is where you've got a significant increase in the resistivity. So this holds with our kind of interpretation of what we were saying previously, that where you've got increases resistivity, you tend to have more intact limestone. Now, I think it's interesting that you've clearly got a drop in this particular borehole here, but actually still the lowest resistivity of this hard limestone is coming in at about 430 ohm meters. And that's higher than most of the weak limestones that we see on site. So we said, well, look, if you've got areas of weak limestone that you know exist in this kind of 6 to 10 meter range and this sort of 350 to 430 ohm meter boundary, let's make a couple of assumptions here about what's going on the site. The first assumption we're going to make is that there is a statistical significance between this particular borehole, which is the one that's mostly sited in the north, which is in the weaker and medium weak limestones, and the rest of the site. So that is to say that our kind of assumption about how resistivity plays out in limestone is true, that we're going to see increased resistivity where we've got stronger limestone and decreased resistivity where we've got weaker limestone. So that's the first assumption we're making. And then the second assumption we're making is that if the limestone between 6 to 10 meters is weak, the limestone above it will also be weak, because if we're looking for dissolution features, which are typically happening from the ground upwards, that's something which we're going to see propagating up. And the reason for that is because as we get towards the near surface and we've got the presence of glacial fluvial materials and sort of various other superficial deposits, we're not seeing quite such a clear distinction in the relationship between what we consider to be pure limestone and the resistivity. So importantly, it means that we can extend that to say, well, actually, anything we see below 6 meters and anything below 340 or 430 ohm meters, we consider to be a risk on the site. And what then is interesting is that if you actually take the locations of some of these resistivity minima, so these are where we have very low resistivity sort of plots, what we've done is we've kind of drilled a virtual borehole, and we've taken that profile out just to show that actually you have at least two locations where you've got resistivity values that would suggest you have much higher degrees of dissolution or clay content, in general weaker limestone than the one that you think might be the lowest at the moment. So what we could do with that is take the 3D information that we have and say, well, actually, so where are the areas where these criteria are fulfilled? And what we came back with was this. So basically, this is a risk map, which we've generated from looking at the resistivity, from making some assumptions about the data and its relationship to the limestone strength. And this is where we can say, look, this is where we think at depth you've got increasing clay that may be associated with glacial fluvial fill-in of old eroded channels, or perhaps where you've got potential sinkhole features. And we asked that question again, is the ground fully characterized? Is the risk design minimized? It may not be fully characterized. I fully think there are going to be uncertainties in here. We've made assumptions, but we've been very clear about those assumptions, and we've been very transparent about the things that we've said. And if an engineering geologist came to me and said, these assumptions are not correct, I'd be very happy to sort of reassess. But I think as long as you can be open and transparent about the things that you've taken into that interpretation, then that's better than sort of trying to be secretive about it or pretend that they don't exist. And so is the risk design minimized? Well, if this holds true, then I think we can at least say where we have areas of the site which are safer for developing, for putting very, very large water-bearing tanks on that won't suffer risk of dissolution, of differential settlement, compared to the areas that may be of much higher risk. And then finally, we were able to sort of integrate this into a video, which I think kind of shows the sort of story that I've told. So we've got these 4 boreholes that characterize the site, and then we're able to do our 3-dimensional survey. We can strip off the superficials. So now we're looking at just of a depth from about 3 meters down, looking down to the ground. Again, you can see where you've got these high resistivity zones, and then this is the low resistivity associated with higher risk, and then you've got the areas which are associated with sort of less risk. And I think what's interesting, if I just go back to look at this, you can see that there are some definite features in here where you've got perhaps very isolated zones of what we would consider to be sort of higher risk areas. So one thing we have asked is for them to go back and drill that to see if that is a sinkhole, because it looks suspiciously like it might be. And importantly, not something you would pick up from the initial geophysical survey that was done at 50-meter intervals. The area down through here we think is actually probably seepage from a pond on site, which is exploiting perhaps a buried channel, which was not known about previously. And then we think up here we've just got some areas of either similar increase of seepage associated through these potentially buried channels, or perhaps increase in dissolution associated directly with the limestone there. And so this was another aspect of this. I talked at the beginning, I opened up by saying about 3D geoscience and the power of using these various tools to communicate interpretations of what we're doing with regards to understanding the ground. And I think that's another aspect of this particular case study, where we've been able to actually take this 3-dimensional data, put it into a sort of 3-dimensional visualization package, and really be able to fully understand, from what we're getting, the impact that these ground conditions might have on the design. So the design engineer can now take this and actually move the footprint of those foundations around and rotate them to make sure they're trying to avoid these high risk zones that we've identified. I just want to round off by just making one last point on sort of data cost and data value, which are sort of related concepts but very different. So I mentioned that they drilled 4 boreholes in the eastern field after the initial geophysical investigation. And what that gets you is that it's about a meter cubed of data. Once you drilled a borehole down to, I think there were 16 or 20 meters, when you actually look at this, it comes to about a meter cubed of data. The 3D resistivity survey, which cost the equivalent of 2 boreholes, so this goes back to the point I was making at the beginning about having integrated approaches and sharing of budgets. That costs 2 boreholes, but you get 500,000 meters cubed of data. Now, I'm not for 1 second suggesting that there's a sort of value equivalence between these two, but I think it's interesting that they had to go on after this to then drill 5 more boreholes. That's what they've done more recently, based on what we found in the 3D resistivity map. So that's another 1.25 meters cubed of data. So as I said, the value of those 2 types of information is not equal. I wouldn't ever suggest that 1 meter cubed of resistivity data is going to tell you anything about the ground compared to a meter cubed of logged core, which is the gold standard of understanding the ground. But a meter cubed of resistivity data is 1 million times cheaper than getting 1 meter cubed of core for the ground as well. So I think the efficiencies here would have been if we'd actually started out from the beginning and said, look, we know this is a site that has got these potentially high resolution geohazards associated with it. Let's do the 3D resistivity first. Let's come up with a sort of geoelectrical ground model which we can look at in 3 dimensions, and then plan the ground investigation. Who knows, maybe we wouldn't have to have drilled those extra 5 boreholes. It might have just been 2 based on the information that we had, because we might have been able to target them based on the features that we found, and maybe the cost of the geophysical study would have paid for itself in the savings. It's something that's very difficult to prove obviously after the fact, but perhaps in the next project we might be able to get some more tangible numbers to that. So with that, I'd just like to say, thank you very much for listening. The main point I've really tried to put across here is that 3D geophysical surveys, they're a source of site-wide holistic models which you can use to make these kind of dynamic interpretations of what's going on the site. Integrating the data and actually taking the information you have from the intrusive investigation, it helps to minimize the uncertainties. It helps to provide multiple lines of evidence that can help you to understand what's going on in the site. And if there's anything I want anyone to do, it's that if you are using geophysics on your projects, please don't just use them as a tool for positioning your boreholes. Try and get someone involved who knows what they're doing with them, who can actually take the geophysical data along on the journey with the intrusive investigation data, and hopefully use that geophysical data to the absolute maximum of its value. I think at the moment we're in this digital sort of revolution of source of information for ground investigation, and geophysics. We've not done a very good job ourselves as geophysicists of touting this remote sensing of the subsurface approach, but I believe that it's something that if we can get the message out there, if we can sort of use these approaches a bit more, it's something that can really help with a lot of the ground engineering projects and challenges that we're facing at the moment. So yeah, thank you very much, and if anybody does have any questions, more than happy to take them.
That's great. Thank you very much, Jim. That was definitely very interesting. Me in particular, as we are planning some geophysics soon on one of our projects. So it's good to give me a little bit more insight. It's one of these things, obviously I'll come across it and try and learn about it, but sometimes it's nice to see how that sort of project worked its way through, because I suspect we might end up taking a similar approach. Yeah, I had apologies if I missed this point, but you said you got a 3D resistivity. How did you manage to get it to 3D? Was it just doing so many close lines at 8.5 meters?
Yeah, so there's actually the terminology around this is really it's not very well defined. So there's many ways you can have 3D resistivity. Some people would have looked at the fence diagram that I said and said that was a 3D resistivity approach because it is presented in 3D. The main difference here is that we've processed it in 3D. There's also a way that you could actually go out and put all the electrodes out at once and actually get 3D measurements from the site as well. But that's probably a step beyond what we need to do for this. So we call this a 3D resistivity survey because we've used a 3D processing algorithm. And you're absolutely right. It's because we've managed to get many, many lines which are close together. And we can then take all of those lines and process them in one go as one 3-dimensional block, rather than having individual lines which are processed and then trying to put them together afterwards. The reason that works is that you're able to basically account for in the inversion the fact that you've got lines that have different measurements, and it means that you can create that, you can have that incorporated in the model, in that model space. If you're using a 2-dimensional inversion only, you're making a lot of assumptions that the ground is basically homogeneous in one dimension, which obviously for a site where you've got potential geohazards just isn't necessarily
can't make that assumption.
So for something like this, the crucial thing is having a 3-dimensional inversion algorithm to get that kind of resolution of data.
Really? So should we be asking our geophysics contractor about that? Anyone else got any particular burning questions? Jumping out. You explained it too well, Jim.
I think it's particularly good, you stressing the need to have an integrated approach, because that so often, well, as you've said, usually doesn't happen. And so many people go into things with an idea that one type of geophysical survey is the only type that can be done. It may not be the best one for that site. I mean, I know a lot of investigations been done using GPR, where GPR is certainly not the most effective on that type of terrain and what they're looking for.
It's probably because it's easiest, right?
Yeah.
Yeah. Yeah, that's something we find a lot. I mean, a lot of my job now is actually going back over historic data and reprocessing and having to sort of pick apart, data that's been acquired under less than optimal conditions. So it's hopefully in time we'll get away from that and we can just get it right first time.
Yeah,
Make
I've
my
been
job easier anyway.
Hearing a lot of that recently about some interpretations and things. And yes, I know some of it is quite sort of time consuming to do. I know in the past when I've done gravimetric surveys, you sort of, you've got to know so many other parameters that are not always recorded correctly.
Absolutely.
Yeah.
I think we've got a question. Do you want to,
Yeah, we've got a hand up.
Hi, James. Can you hear me?
Yes.
Yeah, very interesting talk. I'm
Thank you.
very glad to know that geophysics test is so cheap. So I have two questions. The first one is, what's the how large is the uncertainty of the 3D geophysical profile? Because in your presentation, you have shown us the profile. And the second question is, so they just show us the resistivity profile. So when you process or interpret the data, do you convert? Do you usually convert the resistivity to data to any geotechnical property?
Yeah. Okay. Yeah. Okay. So the first question was related to uncertainty. So I guess there's two types of uncertainty we could be thinking about when it comes to the geophysical data. The first one is what's the uncertainty of our processing. So I can actually share something here which might give you some idea on that. So what we've got here, can you see the screen there? This is data from the project, which I just described. And at the top here, we've got one of those data profiles, which was inverted using a 2D algorithm. So I mentioned to Gemma that you have to make a lot of assumptions about ground heterogeneity or homogeneity when you use a 2D assumption. And the data here at the bottom was using a three-dimensional approach. So this is actually a section that's been taken out, just a single 2D profile from the 3D block. I think what's interesting about these two is that you can see that where we've got this limestone going down through here, the geophysical data doesn't really extend to the same depths as that limestone, which is recorded in the borehole. But when you use the three-dimensional, you can see that there's much more stronger correlation going from the change here. It's not perfect, but where you've got the change in transition from the superficials to the stronger limestone, you can see that's where you have the increase in resistivity, which tends to carry on down throughout that. Now, what's interesting, I haven't actually got. Let me just see if I can find the version which I was looking for. So here, this is, same figure, just with a bit more information on it. But what we've got here, the RMS error, so this is the root mean square error of the model, is actually higher when you use the 2D inversion compared to when you're using the 3D version. So we have a drop of it's only about 0.5%, but it is still you have more confidence in the model result of that. So that's the data side of it. And then the uncertainty, obviously, the next part of that is my interpretation. Now, I can't quantify the uncertainty associated with my interpretation. The only thing we can do with that is to drill and to see if we can actually find the things that I think are there. So that's the bit of this talk which is missing. It's the bit that I'd love to come back and tell you about one day, which is we've had these 5 boreholes which have been drilled on site. And we did ask them to go and put a borehole through what I think is a sinkhole that we found in the data. And if we come back and it finds that they found a sinkhole, then I guess that shows that the uncertainty associated with interpretation is pretty low. If we haven't, it shows the uncertainty is pretty high. But that's the only way we can really test the interpretation, is to go out and actually drill it and find out what's there. So that was your first question, I think, and then I've already forgotten what the second question was, I'm afraid.
The second one is, do you usually, in practice, do we usually convert the restricted data to any geotechnical data?
So it's not something I've seen done in the sort of in the commercial sphere so much. So when I used to work at the British Geological Survey, that's something they've done a lot of research into, and it's particularly when they use resistivity monitoring systems. And the reason for that is because you're normally deploying a resistivity monitoring system because you want to see changes in resistivity associated with moisture content. So what you can do there is you can take some samples of the material that you're monitoring, you can take that to a lab and you can look at how the moisture content changes and what effect that has on the resistivity. And when you have an understanding of that, you can then basically convert your resistivity measurements into an estimate of the moisture content. And if you want to go further than that, you can actually start to look at converting it to things like pore water pressure as well. And from there, if you want to go further, you can start looking at how the pore water pressure might relate to, say, suctions, or in a sort of landslide environment, or perhaps trying to estimate directly sort of shear strength from that measurements as well. But again, the big caveat with that is the transmission of errors through each of those modeling processes. So there's already quite a lot of uncertainty wrapped up in your initial geophysical data. By the time you've taken it to maybe 1 or 2 transforms to get, say, close to sort of shear strength estimation, you've obviously had uncertainties associated with, selection of soil samples, or the sort of sensitivity ranges of looking at moisture content versus resistivity in the laboratory, how that scales up, the anisotropy of looking at particular soil samples. So it's a really useful tool for understanding broad scale changes. I think generally speaking, conversion of geophysics to these geotechnical parameters is a very useful tool for looking at broad scale change and perhaps communicating that broad scale change to sort of engineers. But estimating or trying to get refined geotechnical parameters from geophysics, I think we're still quite a long way from that. I think it's a really interesting area of research, but it can be quite, you can inadvertently give someone a lot of confidence or not if you start estimating geotechnical parameters from geophysics without lots and lots of detailed data to back up the conclusions you're making.
Yeah, thank you. So quite helpful. Thank you.
Have anyone else got anything else? Anyone else? Have you any other questions? I think that might be it. Well, thank you very much, Jim. That was really interesting. I think it sounds like we've got a few people who couldn't join, so I'll send the recording out afterwards.
Jim, just before we go, Jim, David's asked whether it'd be okay if you can send in any questions at a later date. You'd sympathise with this because he had to do parental duties in the middle. He's going to listen to the recording.
Yeah, that's absolutely fine. Find me on LinkedIn. You can ask me directly there, or if you want to pass them through yourselves and then pass them on to me, I'm very happy to take any questions.
Right, thank you.
Lovely stuff. Well, thanks so much. I appreciate the offer to present, and it's nice to have a captive audience who are here to listen to what I've got to say. So yeah, thank you very much, everyone, for coming along.
Yeah, thank you, Jim. It's always a bit difficult and Zoom sort of interaction there, but yeah.
Yeah, it's been brilliant. Well, very clear. Just perfect, really. And Gemma, you needed to get all the rest of your people there to listen to it.
I know. It will be distributed. Great. Thank you very much, Jim. Yeah, we'll leave it there. So.
Thanks very much.
Thanks.
Have a good recording, Leslie.
Yeah. And bye, everyone else.
Bye-bye.
Cheers. Bye. Thank you, everyone who came.
Thank you. Bye-bye. So Leslie,